So let's welcome George Andrianakis.
Hi. Hi. Can you hear me? I guess so. Hi, I'm George. I work for Red Hat for the past year, and one of the things that we've been working on the side is Istio. So I would like to talk about that today. Basically, we'll see what Istio is, what problems it tries to solve, and some like high-level stuff of what it can do and what the architecture looks like. So, any like cloud native talk these days has to start with microservices. So, this is all about solving problems with microservices. And what are the problems that microservices are? We all know what the benefits are, but we sometimes don't stop to think like what the fundamental problem of microservices is. The fundamental problem is that microservice architectures are basically distributed systems. And distributed systems brings in a whole class of problems that we simply did not have when we were developing our monolithic applications. So these two tweets here basically sum up, like in a humoristic form, what the actual problem is. That when we had our great monoliths, all we did was method calls, and things simply didn't fail because they were inside the same machine, just memory calls. Now, though, most calls, well, actually, a lot of calls that we make go through the network. And the network, as much as we prefer to think of it as something that will never fail, that is simply not the case in our cloud providers. So we need to think of creative ways of overcoming these problems and building features like resiliency into our microservices architectures. So what are the basic challenges we face when we're developing microservices and by distributed systems, since microservices are distributed systems? Our basic problems is, first, we need to deal with resiliency and fault tolerance. So how do we do that? We usually use retries and timeouts, or more advanced things like circuit breakers. Second, when in cloud native applications where our services come and go really quick or can be auto scaled, like with Kubernetes, like we heard in the previous presentation, we need to know dynamically which downstream service we are going to call. And that has to be done in a load balanced manner in order to avoid overwhelming certain services. Now, we also have to think about how we're going to debug these applications, because we all know that there is no system without bugs, and there's all the problems that we are going to face are always going to happen in production. So we need to think about ways to overcome, to enable us to debug certain issues. And we use logs, metrics, and traces. And in like circa 2017, 2018, the buzzword is observability. Also, a large like enterprises usually have certain policies around security and policy enforcement. Like when we're running our stuff in the cloud, we want to make sure that service calls between services happen in a secure manner. That in microservices, that means they happen over HTTPS. So any services that might be running co-located with our services cannot eavesdrop on our network traffic. Policy enforcement means that we, in large organizations, we want to be able to limit the calls between microservices. So if we have like 50 different systems, we don't want every microservice to be able to call every other microservice, because that could create security issues. And finally, with the whole host of services we have, we have new opportunities to shape our traffic in order to do things like make our deployments more secure, or like test different business like problems by doing like A/B testing. So how do we deal with this complexity? And I want to note that these problems are not new. These problems existed when the pioneers of microservices started developing these systems. The pioneer that most of us are aware of is Netflix. So what Netflix did a number of years ago, when awesome systems like Kubernetes or Apache Mesos didn't exist, they took the approach that most of us would take if we were called on to solve these problems. What they did is they created libraries, and they created various applications in order to deal with these problems. So they created libraries like Netflix Hystrix, which enables circuit breakers and bulkheading inside applications. Also Netflix Ribbon, which is a client-side library that is embedded in our code and tries to client-sidely load balance between services. And they also created systems like Zool and Eureka to enable such features like service discovery and edge-side routing. So what are the problems with this approach? I mean, let's say that we created our library and our library basically, and we try to embed it in our microservices. What are the basic problems? Oh, sorry, before I move on to that, some of you probably have used Spring Cloud, so you're saying, oh, right, this stuff is a lot easier now. All I need to do is start a couple of Spring Cloud applications with a few annotations, and things magically work. And that's basically true, but the problems are later on, as we'll see, with the libraries and the systems that are depicted here, is that we have our services on the right, the services like what we write our code, and inside those services we have a whole host of different libraries that try to implement the features that we mentioned earlier. And on the left, we have a few purpose-built systems that handle the server side of things, and all this runs on our cloud infrastructure. So the problems, the main drawback that you can think of is that, okay, if I'm building a library in a certain stack, like let's say I'm building a Java library, that Java library is not going to work for Node.js applications. It's not going to work for Python applications. If I wanted to build microservices in multiple environments, I would have to build these libraries in a consistent manner across all these different runtimes, which could severely limit one of the features that microservices has, that each team can supposedly pick up their own stack and write their applications in their own stack, and everything works. So when we have to build libraries in certain languages, that really limits our ability. Second of all, these libraries are complex. They solve complex problems, so they're obviously going to have bugs. What we need to do is to be able to apply these fixes to these libraries in a consistent manner. So what we don't want is to have 100 different microservices running 5 different versions of our libraries, because then we won't apply our knowledge of how to solve these problems in a consistent manner. So we need to find a way to apply fixes to these libraries across our whole system. And third problem is that maybe a lot of you who have used Spring Cloud will see that you might be writing like 20, 50 classes of your own code and saying, okay, great, it shouldn't be a big library, a big application or anything, but you end up with a 50, 60, 100 megabyte Uber jar file, and you're like, what's up? I only wrote like 50 classes. And that could severely limit your network traffic and how fast your applications can start up and everything. So in the age of Kubernetes, we are thinking about there must be a better way to solve these sort of problems. And the better way that we have come up with is that we want to move the logic of solving these problems, solving all the concerns that we mentioned earlier, we move them out of our application and into the platform. So what the ideal scenario here is that our application code will just serve and implement our business logic. It won't contain any code of how to solve these network problems like the resiliency and all the rest. So that gives us the ability to apply the knowledge that we have to all microservices inside the platform. Really quick, the benefits that we have is that the holy grail of microservices, that each microservice can now better focus on what it's supposed to do, which is bring business value and not solve distributed systems problems. We can have heterogeneous architectures where some team builds in Node.js, another team builds in Go, somebody builds in PHP or whatever, and that will just work in our system. And then the final benefit is that we can consistently apply all our policies, the policies we have selected, to our whole distributed system architecture. Now, for those of you who were in the previous talk about Kubernetes or who have experience with Kubernetes, you'll be thinking, okay, great. I mean, Kubernetes provides some great things, but it doesn't solve all the problems that you mentioned in your previous slide, and that is absolutely true. And this tweet on the right captures that sentiment that Kubernetes was never intended to be the top layer of the platform architecture. It was meant to be an awesome platform that, as Pascal mentioned earlier, is extensible and we can leverage to solve various problems. So on the left, you see the various problems that we need to solve and what Kubernetes brings to the table. And now we need to think about what are the other problems. The other problems that we mentioned are what Istio tries to solve, like the resiliency, the policies, the security. Those are the problems that Istio tries to solve by building on top of Kubernetes and filling in the gaps that are deliberately left open by the Kubernetes platform. So the basic thing about how Istio attempts to resolve these problems, if you're gonna like take away one thing about Istio, how it works, it's the following: that Istio is comprised of a host of network proxies. So as was mentioned earlier in the Kubernetes talk, each of our applications are not deployed as Docker containers. They're deployed as pods. What a pod is one or more containers. So definitely each pod will contain our application code, but now when we use Istio, our application code is one container, but there's always another container that contains the Istio network proxy. And what that network proxy does, it intercepts all traffic that comes in or goes out from our service. That means that Istio is aware of the entire traffic, the entire, let's say, level 7 network traffic that is going through our microservices architecture. And being in that position to intercept all traffic gives it the ability to apply all the different policies for solving the distributed systems problems that we like. And just for a quick note, in Istio, the network proxy that is used by default is not Nginx or HA proxy that you might have heard of. It's a newer network proxy, a lightweight network proxy called Envoy, which was a project started at Lyft a few years ago. And the great thing is that it's real lightweight and it's very configurable. So, and it's small and it can be embedded very easily inside a container, which is the reason why it was used and selected as the default proxy for Istio. So let's say we're running like 100 microservices, 150, 200 microservices. That means that we have 100, 150, 200 network proxies running alongside our application. That immediately creates another problem. It creates a problem: how do I manage all these network proxies? And that's where the definition of the service mesh enters the picture. The service mesh is a decentralized application networking infrastructure that sits between our services and provides us the ability to solve all the network problems that we were talking about earlier. And like, let's say the cloud native parlance, the service mesh is composed of two let's say components, whatever. One is a data plane, which is the network proxies that we were talking about earlier, and the other one is the control plane. We'll see this in the following slide with a high-level architecture of what Istio looks like. So Istio.io is the main site, and Istio is considered like a control plane for the service proxies that we were talking about earlier. And here's a very high-level architecture of what Istio looks like. Istio is a complex beast that any of you who have tried to use it or have understood its benefits and read up more, have understand that this is not a simple system. Kubernetes itself is complex, and Istio just adds more complexity but solves a whole host of problems. So we'll just go over the very high-level architecture. On the top of the picture, we can see the control plane. The control plane is where we actually enforce our policies and our knowledge of what we want our distributed system to look like. And it's composed of multiple components in the control plane, the most important of which are the pilot, the mixer, and the citadel. The pilot essentially listens to the Kubernetes API, and it exposes its own API to which we apply our configuration, and we'll see what kind of configuration that is later. The mixer receives metrics from every network proxy inside our service mesh. We can see that with lines from Envoy to the mixer, and it also contains it responds to queries of whether like a network call from service A to service B is allowed or not. And the third important component is Citadel, which is used to push HTTPS certificates to the Envoy proxies, and also handles like rotation of certificates and stuff like that, so us as developers don't have to deal with such problems. So let's quickly compare what we used to do without Istio for distributed systems and what solutions utilizing Istio look like. Keep in mind that the high-level idea for Istio is to move the solutions to distributed system problems outside our application code and into the platform, and that's what we'll see right here. So let's say using the Netflix stack that we mentioned earlier, or the Spring Cloud implementation of that Netflix stack, what we would do is in each of our microservices, like service A, service B, service C, we would embed the Hystrix library inside our application, and we would write code inside our let's say our services where we were calling service A. From service A we wanted to call service B, and that obscured the simple logic that from service A we wanted to call service B. Now inside our code we have all these various layers just to handle circuit breakers. So what Istio does is that it says, since our application is going to be running in a pod, I'll run Envoy proxy next to the application that will intercept all our traffic, and it will apply the circuit breakers on its own. So our application has no, whether it's a Java application or a Node.js application or a Python application or whatever, it has no extra code implementing circuit breakers inside our source code. All it has is a call from service A to service B. The application of the service breaker, or the policies that we want, like when a circuit breaker is supposed to open or close, are embedded inside the proxy, making our source code a lot simpler. Most of you who have been building microservices will definitely have to, at some point, reason about how timeouts and retries are applied in our microservices, and that's usually done like either using libraries like RxJava or hand coding our own solutions inside our source code, just to be able to, let's say, retry our network calls when something unexpectedly goes wrong, and it will go wrong in the cloud. So, and that again obscures our source code. What we want to do again with Istio is that we can just have a simple network call from service A to service B, and we can configure to Istio and tell it that, okay, calls from service A to service B can take up to 15 seconds maximum, and we retry a total of 5 times. Let's keep in mind here that Istio, despite all these awesome features, can't guarantee us that our system will actually work no matter what. I mean, if the network from service A to service B is down, let's say service A and service B were different availability zones, and the network was cut between those. No matter how many times we retried, the network won't come back until until our cloud provider fixes it. So again, our services still need to reasonably handle errors, and that's a major concern in any microservices architecture. But what we've taken out of the picture is we've taken out the plumbing for different types of network failure. No, we still need to handle the failures, but we've taken out plumbing of how we deal with the distributed systems problems. Any of you who have worked with HTTPS, that you definitely know that this is something you don't want to do in your code. It's not pretty, especially those who do this in Java, as I've done. It's not cool at all. It requires a lot of setup, and we're not even talking about how you're supposed to rotate certificates that expire and stuff like that. So this is something ideally that I personally would never want to do, and that's what Istio gives me. It gives me the ability to write my code like I was just making a regular HTTP call from service A to service B, and then Istio will transparently intercept the traffic, apply HTTPS from the service A to service B, and will automatically get secure network communication between the two. So as you can see, already Istio is giving us so much out of the box that we do not have to write in our application code. Another thing that we've seen a lot with microservice architectures is trying to make our network calls more dynamic from an originating service like service A to, let's say, multiple versions of service B. What we usually did up until like before the Istio era, was to have a dedicated component between service A and service B that would handle these calls, will intercept these calls, and where we would like apply, let's say, Groovy scripts in order to decide where the calls should go. And this was like a single point of failure, and also a single point of where all our application code would, all our routing code would end up, and it looked messy. So with Istio, there is no other entity in the middle. All we need is to utilize the network proxies that we already have. So the Envoy proxy can receive configuration. Let's say for HTTP requests, it can handle cases where, let's say, an HTTP header, a special HTTP header is present. Let's say if, like, I'm user George, I can say when that header is present, I want you to redirect all the traffic to the new version of the service B. And let's say one reason I would do that is because I want service B is like the new version. I want to check it out to make sure everything is okay before everybody else, all my clients, see it. And that it has multiple rules that can be applied in order to route such traffic. Variation of this scheme is like to use A/B testing, where we could tell Istio that I want half the traffic to go to the old version and half the traffic to go to the new version. I could do this like to perform tests, see like which version of my service responds better, either technically like faster, or to see like what clients would respond to better, which version they would respond to better. And another feature that some like DevOps shops try to implement and is not easy is to use dark launches. Dark launches is that we have a new version of our service running inside the cloud, inside the cluster, but we don't want it to receive, actually we don't want it to take away any traffic from the already running service. We just want it to receive all the production traffic, because we have all our observability like metrics and logs enabled on that, in order to see with real production traffic how that actual service, how that new version actually behaves. Because we all know that, okay, all our stuff runs great on our laptop and we never have any problems because we're great developers, but once we move everything to production, stuff just breaks down because things happen, traffic, real world traffic is not what we anticipated. So using dark launches enables us to see real application traffic without affecting the actual production system. A trend that has also been introduced by Netflix in the microservices era is to use chaos testing, which means that we actually break the network and break our services on purpose in order to see how our system as a whole, how our microservices system as a whole will behave. So we go, what Netflix does, since they're an AWS shop, they have integration with AWS that like takes down virtual machines, takes down the network between them in order to see how the system as a whole will behave. And this is like very sophisticated stuff, and they have special systems that are used just to enable this kind of feature. With Istio, since we already have our proxies in place, it's super easy to implement chaos engineering features without having to set up a complicated system like Chaos Monkey and Spinnaker. So what we could do is we could say a network like an Istio operator could apply a rule that says all or like 10% of the traffic from service B to service C will receive an extra 10-second delay. I mean, all our services, when we run them locally, will run great because between our services on our own laptop, there won't be much delay. But in a real cloud situation, such kind of delays could easily occur. And we want to simulate that so we can be prepared when that actually happens in production. So with Istio, it's super easy to simulate such scenarios, like introducing a 10-second delay or introducing HTTP errors that we didn't expect previously. Like, let's say we are responsible for building service B and another team is responsible for service C, and we want to see how our service behaves if like a deployment to service C that the other team did went horribly wrong and it starts returning HTTP codes that we didn't expect. So what Istio does in this case is it makes it very easy to simulate such kind of failures. What it doesn't do is it doesn't give us any tools of how to handle these sorts of situations. So what we're supposed to do after that is take these failures and like apply the knowledge in a way that will improve our services. Most of you who have used distributed systems and built microservice architectures have probably found distributed tracing invaluable for your debugging ventures, and you usually do that by, in at least the Java Spring world, you would usually embed Spring Cloud Sleuth as a library into your application, and then you'd be running a Zipkin server somewhere and collect traces. So that means you'd again be adding a library into your application just to collect traces from which means that we're gathering metadata from what call originated from which service and ended up in which service and how long it took. What Istio does, it makes that a lot easier because again the service proxies intercept all the traffic, so they have all the knowledge about which call started where and where it originated. So again, without libraries, we can collect our distributed tracing metadata. This distributed tracing feature of Istio is the only feature that actually requires a minor modification to your source code in the means that you need to propagate special HTTP headers in order for this to work. All the other stuff we saw, you don't have to do anything in your application code to get it to work. This is the only thing that requires minor source code adjustments. And before we close the session, I'm going to want to show you some little eye candy. This is not going to be a ton of YAML code that all of us building distributed systems work with. This will be clearly pleasant stuff on the eye. So this is a Grafana console. What Grafana does is show you an awesome dashboard of how of different metrics that we are. Without Istio, we would have to build this console and make sure that all the data that is in that corresponds to our microservice ends up in this console somehow. What Istio does is that it sets up Grafana and Prometheus, and it automatically forwards all the metrics in our network to this console. So in this console, we can see overall picture of how our network is performing, like various HTTP codes or how long the mean time between services is, or we could break it down between services in order to get an even more granular picture. And all this happens out of the box. You don't have to do anything. It's set up automatically. Of course, you can configure the dashboard the way you want, but even out of the box, you get an awesome picture. This is the distributed tracing dashboard that you again get out of the box. That we can see, like in this microservice architecture, there's actually three applications. There's the customer service, the preferences service, and the recommendation service. And a call that originates in the customer actually ends up in the preferences. So in this graph form, we can see what an initial call to a customer's microservices looks like when it ends up actually into the recommendation, how long things take. So this dashboard is set up out of the box. All we need to do is enable the small HTTP header propagation that I mentioned earlier in order to get this awesome picture, which is invaluable for debugging purposes. And the last slide I wanted to show you is a system that actually Red Hat is developing. It's called the Kiali. For those of you who speak Greek, you'll immediately understand what Kiali means. Kiali is a monocular. It's a Greek word for monocular. And what it does, it gives you an awesome, it's like a UI into how your network is configured, how your service mesh is configured. So it will give you UI like which versions of the service have a link to which other versions of the service, and it'll also show you show you metrics for the services you have configured. There's also an awesome demo of this. It's got like a lot of animations and stuff, and gives you really a great overview, a really great UI to understand what your links actually look like. And even Istio isn't limited only to HTTP level 7 network calls. There are actually adapters that you can implement in order to, like, let's say, proxy traffic to a MongoDB. So in this picture, if I had a MongoDB, the MongoDB would also show up in this picture, and I would know just by looking at it, like, let's say I was a new architect at the company that used this, I could immediately understand that, okay, this microservice uses MongoDB, all the rest just connect to it. And connect to the other services. And that's all I had for today. These are various links that you could find a lot of resources about Istio. Istio is a complex system. This was like a very high-level overview, very quick. Any of you that actually want to use it or thinking of using it will have to definitely do your homework and make sure you understand your stuff before you start using it in production. That's all I had. Thank you very much. So I don't know if we have time for questions. I guess we do. So yeah, let's go ahead. Do we have a microphone?
Thank you for the presentation. Correct me if I'm wrong, but I understood that these proxies are separate network nodes in the cluster,
No,
right?
they're not, no.
They're not?
They run inside the same pod that your service runs.
Ah, they are inside. Okay, so that invalidates my question, so thank you.
Yeah, the person right behind you. So.
Hi.
Hi.
Thank you for the presentation. What's the performance impact on the whole thing?
That's a very good question, actually. So, Istio was like released to 1.0, maybe I think during July or August, So there were definitely studies on the impact of having proxies within each call. I think those numbers were like maybe like 5% increased network latency. And as new versions of Istio coming out, so now we're like at 1.2, as newer versions 1.3, 1.4 will be released, performance will definitely be an area of focus. So far, the focus was on making Istio feature complete, so performance wasn't at the forefront, but it's not. It doesn't have a large impact, but it definitely could be prohibitive for a certain class of applications that are very latency centric. Anybody else?
Hello, really nice talk. We are using all those technologies in my company, and especially Istio is fantastic. So I've got a question related to the circuit breaker pattern you mentioned. Can Istio replace a technology like Hystrix? As an example, with Hystrix, you can wrap calls to a Redis cache or to SQL databases. Can you do this with Istio, or is it only for HTTP calls or gRPC?
That's a very good question. First of all, I want to start out saying that what Istio calls a circuit breaker is not exactly what Netflix calls a circuit breaker. So what Istio calls a circuit breaker, usually Netflix I think would call a bulkhead. So let's start there. But Istio is, in its current form, it's limited to HTTP and gRPC network calls. So there are certain specific implementations for Mongo, but that's because someone actually cared and went and wrote those adapters. So if you wanted a Redis call or something like that, then you would probably have to do it yourself. It's not that it's not doable, it's that no one has done it yet. And because this question has come up some other times I've given talks, we're not talking here with Istio, we're not talking at all about messaging microservices. So anything that's queue related is not Istio. Istio is only about direct HTTP or gRPC communication between microservices. So anyone else? Okay, cool. I guess I'll be available for whatever other questions you have. So thank you very much.